Hello everyone, I'm Anindya Mondal and I have been an undergraduate student in the Department of Electronics and Telecommunication Engineering at Chatterjee University, India. Today I'm going to present my work, Recovery of Missing Sensor Data by Reconstructing Time-Varying Craft Signals at the European Senior Processing Conference 2022 held at Belgrade, Serbia. We organize our presentation as follows. In recent years, we have found a widespread application of wireless sensor networks in various fields. The primary reasons for their widespread application include their low cost, small size, low power consumption, and easy for deployment. Often these sensors are deployed in remote locations, and some of these nodes can get damaged due to environmental or human intervention. And hence, replacing these malfunctioning or inactive sensors may become a tedious task. So accurately reconstructing these missing values is the only way forward. In recent years, we have seen multiple approaches to tackle this problem of reconstructing the missing data. Some of them are based on the k-nearest neighborhood, expectation maximization, low-rank matrix completion, and probabilistic matrix factorization. However, most of these methods give suboptimal performance when a sizable amount of data is unavailable. The reasons may be that they fail to properly utilize the embedded spatiotemporal dependencies in the sensor data. Our method improves upon the previous methods up to a great extent. So before moving on into our work, let us discuss the primary contributions of our paper. So in recent years, we have seen a widespread application of cloud-based methods in various domains like computer vision, biological and social networks, infectious disease prediction, and many others. The primary reason behind their widespread application are the ability of graphs to capture meaningful information from data lying on irregular and complex structures. Graph signal processing is one such graph-based technique. In graph signal processing, sampling and reconstruction of graph signals plays a vital role in various real-life applications. In our work, the graph vertices represents the relative position of the sensor nodes, and the vertex index signals represent the sensor attributes. To summarize our contributions, we introduced the concept of reconstructing time-varying graph signals to recover missing data in wireless sensor networks. Our work is inspired by the 2020 Machine Learning and Workshop paper, Machine Learning of Signal Processing Workshop paper by Gerald and others. In that paper, they predict the number of new COVID-19 cases by extending the sublevel norm defined in graph signal processing for time-varying graph signals. Here we utilize the sublevel method for the recovery purpose. This method shows significant performance improvement over state-of-the-art, and we validate our claim by performing experiments on multiple publicly available datasets which are collected from diverse environments like both indoor and outdoor environments. Now we discuss the proposed algorithm. Before discussing algorithm, let us discuss some basics of graph theory. So we have a graph which is basically we have a D as the set of vertices and epsilon as the set of edges and W as the weighted adjacency matrix. The weighted adjacency matrix explains the connectivity of the nodes in the graph. D is the degree matrix, which is a diagonal matrix, and L is an unnormalized Laplacian of G, which is basically the difference of the degree matrix and the weighted adjacency matrix. Also, we have X, which is a real valued vertex index graph signal, and it is shown in the figure below. As we discussed earlier, sampling and reconstruction of graph signals is a property or useful property of graph signal processing, and it helps applying graph signal processing in various domains. Here we can see theta is a sampling operator, so what theta does is that it performs the sampling of some of the nodes of the graph. After that, we can see phi as the interpolation operator, which finds out or interpolates or reconstructs the unavailable values from the available values we have. So in our work, we model the missing sensor data recovery problem as the reconstruction of time-varying graph signals. We perform the reconstruction by minimizing the sublevel norm of time-varying graph signals. So in the work, we have a sensor networks with many sensor nodes, and each sensor records a certain attribute, let's say the temperature of a specific geographical region over the span of a year. So it may happen that some of these sensors may be defected or damaged, for which some of the values will not be available for any sensor for any specific time. So using the sublevel algorithm, we are trying to reconstruct those unavailable values we have. In our work, we have made some prior assumptions. For example, here we assume that the graph signals are smooth in space and time. This means that we have assumed that the nearby sensors have similar readings and changes in readings are not abrupt with time. Now we move into our work. So basically, X is a matrix where is a time varying graph signal where each element xt denotes the signal value at time t. Here, each row of X represents a time series on the corresponding vertex. In 2017, Q and others defined a smoothness function S2X, which is basically the trace of the product of the transpose of matrix X, the Laplacian, and the matrix X itself. The expression here comes from the sum of all the Laplacian quadratic form of each graph signal. Q and others also defined a temporal difference operator DH as shown here. The temporal difference operator, when it is multiplied with the matrix X, gives the temporal difference graph signal. So this is basically the array or the matrix of the difference of the values of the graph signals in between each consecutive time. For example, here you can see it is x2 minus x1, x3 minus x2. So basically, each element is the difference of the nearby or nearby graph signals or sensor readings in our work. They also define a matrix J, which is the sampling matrix. In 2020, Kiraldo and others defined the sublevel norm for time-varying graph signals, which is basically a trace matrix as shown here. It comes from the sum of all the sublevel norm for each graph signal, and L is a symmetric matrix. Finally, we formulate the sublevel reconstruction problem for time-varying graph signals based on the work of Kiraldo and others, as shown here. It basically consists of two parts. The first part here, that is this one, which is basically error term, and the second one is the sublevel norm term. The first term, which is basically the minimization function term, basically it reconstructs the original values of the unavailable values or the unavailable sensor readings as accurately as possible using the available values we have. The second one, it incorporates the temporal difference operator. So basically, the temporal difference operator helps to incorporate the spatial as well as the temporal information. So based on these two terms, as shown here, we finally formulated the sublevel norm reconstruction algorithm for time varying graph signals, which helps to reconstruct those unavailable values we have with us.
Hello, my name is Mayukhmali. I will be presenting the remaining of the slides. We have evaluated our proposed methods on the publicly available datasets like Molen dataset and Intel Lab dataset. The Molen is an open access dataset of hourly weather observation in Brittany, France, while the Intel Lab dataset consists of the data collected from 54 sensors deployed in the Intel Berkeley Research Laboratory. We have compared our proposed method against state-of-the-art data recovery approaches like KNN, EM, LMRC, and PMF. In our work, we removed random data points from each of the datasets and then using our framework, we tried reconstructing those missing values. The values thus generated were compared with the corresponding original values using metrics like MAE and RMSE. Here, we show the quantitative comparison of the state-of-the-art methods versus the proposed methods. The base results are in bold. Here, by sampling density, we mean the amount of available information. For example, sampling density of 0.1 means that we have only 10% of the data available and we need to reconstruct the remaining 90% of the data. Here, we show the RMSE and MAE plots. It clearly shows that even under lower sampling density, the proposed method delivers consistently better performance. Finally, to summarize the whole work, we apply the concept of time-varying graph signal reconstruction to recover missing data in sensor networks. It leverages the concept of a recently introduced method based on minimization of the Sobolev norm of time-varying graph signals. This method surpasses multiple previous approaches in the reconstruction accuracy, especially during the unavailability of a big chunk of data. In future, we can extend the method to include non-smooth situations. Here we mean situations where nearby localities have drastically different temperature or changes in temperature are abrupt with time. We can apply graph learning based methods to attain this goal. Thank you for listening. Let us know if you have any questions and want to know more about our work.